Come on. Hong Kong. I'm from King Kong. Hello? Hello?
Hi, Christopher. Hi, how are you?
Oh, I'm good.
Okay, great. Okay, so we said last time that you would like to do some work on past papers, and I suggest we split it in two. First, we do a couple of questions from what we discussed last time, atoms, particles, and then the second half we're going into past paper. Is that okay?
Yeah.
All right, okay. And let me share my screen. Okay, I mean, there's many questions, but as we said, we want to stop after the latest 45 minutes. And there's a multiple choice paper as well, but I think it's easier to start first with structured questions like this one. Oh. So, actually, this one goes straight into the emission of particles. Nucleus X, we don't know, doesn't matter really. It decays by emitting beta particle, as a beta plus, and forms a new nucleus. So 1123. And when we look into the equation, what you have to do quite often is you have to only, of course, state here the number of protons and the number of neutrons in nucleus X. So we can do this, but I would like to start with X, the typical decay. So, and we start with the sodium, 1123. Oops. 3. So, into what does the unknown nucleus decay?
The positive electron.
So, yes and no. What is the? What does it say? Into what? What does it emit? What does that unknown nucleus emit?
The positron.
Okay, the beta plus. And what? How do we have to take charge and mass of that?
0 and 1.
Okay, all right.
Plus
So,
1.
yeah, plus or minus?
Right? Plus 1.
Plus one, yeah. And it's the plus. And what else is it emitting?
The electron neutrino.
All right, so that is sometimes asked as well. It obviously not explicitly not being asked here, but it helps to write it down, respectively, good exercise. So how many protons do we have?
Before is 12.
In nucleus X. So in X, huh? So we want to know the number of protons and neutrons. So in other words, we want to know what element it is, or what atom it is. Going backwards, so to speak.
Should be 12.
12, okay. And hence, how many neutrons?
11.
11. Okay. So what would that be?
Calcium.
For
Oh,
calcium or
no. Magnesium.
magnesium, right? And just, I mean, if the result is a sodium with 11, so where will it be, left or the right, on the left side or on the right side in the periodic table, so to speak?
Huh?
I mean, you answered the question already, but just because we are talking about 12, sodium has 11, so in which actually group will the new or the previous one be?
Sodium is on the left.
Okay, yeah, exactly. Okay, no, all right. Huh? So actually, we have the fantastic thing which many chemists, well, they were not really chemists, in the past tried to achieve, make gold out of something else. For example, lead. So here of course, we don't have gold, but we see that another element is forming. Huh? Obviously, because it's losing a proton. Okay. Question could be phrased around that as well. So, what is the similarity between beta plus and beta minus particle?
Huh?
So, when you look at question 1b, what could we name as a similarity between a beta? We know that there's a beta plus and a beta minus.
The mass.
The mass, for example. Oops. What else could it be? I mean, you only have to give one, but what else could it be as well? When you think of the magnitude of something without, and forget about the plus and minus.
The charge.
Charge, exactly. All right. And of course, we don't have to be that precise. That's fine when we say mass. But of course, ultimately, we talk about the rest mass. That's just a small detail. So that's just to give an idea that mass is not exactly mass eventually. Huh? We talk about the rest mass. Now we go already into particles. That may happen. And has nothing to do with the previous question. What is the quark composition of a meson?
Meson is quark and antiquark.
Okay, all right. Quark. And what does, in that context, what does the word anti say, anti or anti say or indicate? What information is there?
It's the opposite charge of the normal quarks.
Okay, huh? All right, okay. It can be various things, not in this context. So it's basically just the opposite. So that's why, of course, antimatter sounds a bit scary, but it's just the opposite of what we are talking about. That doesn't make it not matter. So the deeper we dig in, the more kind of challenging and interesting it gets. All right, now here we go into hadron because of two down quarks and the charm quark. And what is the charge of the hadron? And we have to show how we come up to that result.
Two down quarks is negative, so 2 times negative 1/3. And then charm is plus 2/3. Elementary, both are
Okay,
elementary
right.
charge.
Okay, so the down quark is 1, and the charm Q is just plus 2/3. And what is the next step? I mean, because we have to show our working, so we should not just jump to the final result. We should show the next step. Yeah? Also, it's very obvious, but still.
So just add them together.
Okay, yep. Exactly. So we can already say 2 times minus 1/3 plus 2/3. And of course, make it each time. Don't forget the electron. That's important. So we can, of course, simplify make our life a bit easier. Just adding it at the outside. Or we can add E every time. Or we can even say minus 1/3, minus 1/3, plus 2/3. That's really doesn't matter as long as it's correct in the end. And answers, what is the charge?
0.
0, huh? That's something quite. I mean, if you think about it, like, okay, we have a so-called uh, particle or below particle kind of, and it has no charge, but it has mass. So that's why all that is so kind of fascinating. Okay, now we go into kind of a little bit of an experiment. So So we have the thin metal foil, but the arrangement is a bit different, kind of, than what you may have seen before. It just gives you time to read the whole thing. There's a bit of information overflow.
It must be a vacuum because
Vacuum? Yep.
the alpha particle will be blocked by the air.
Yep, exactly. Blocked just by air particles already, right? I mean, O2, CO2, whatever, right? Exactly. So it's very sensitive because it's quite big, hence it bumps fast into something. I mean, not very scientific, but that's how kind of it works. Okay, we probably have to go back to this one now. Question 2b. Why the readings detected by D? So we have the detector D, and the conclusions that were made about the nature of patterns. So we have to explain the readings and the conclusions that were made. Look, just go back. Write it down. What is happening at W and what is happening at Y? Let me just quickly scroll. So okay, it's 4 marks. So that goes quite deep already into the matter. But it helps if you just look of what you analyze of what you see, what with what you know, then I think it's the answers.
Well, what's the question on the other page?
Okay, yeah, sure. The question is pretty far-fetched. I mean, it helps in just such a context to basically go back to the original experiment, think of it a bit, say, okay, what did they observe? What was so astonishing when they made those experiments, respectively saw the results of it? It was kind of not really expected, right? Of course, now we know, but then they didn't. So they were really focusing on what they saw, which is science. And
W should have a very small reading.
Okay.
Because the chances of the alpha particle being reflected by the nucleus of the gold would be very low.
Very good. Yep.
And X would have the highest reading because in between the nucleus, the nuclei is basically is mostly space, empty space.
Yeah. Okay. Great. Yeah. Very good. That's exactly. Yeah. Very good. That's a good combination of what we kind of know, of course, and from what we can say here in context, or what the scientists at that time had to conclude. Say, otherwise, I don't really see why it should be like that, right? And it was totally contrary to what they expected. That's actually not to forget. And of course, it doesn't stop. We continue with that. Also, we empty space. We observe. We have come very far in the last 100 years. That's for sure. But there's still many things, and of course, we always have the same questions: what do I see? Does that match with the model I have? And eventually, why not? Answer: what else could there be? So Big Bang is a good example later in the 60s, right? For example, black holes is another one. The Higgs boson. There's always something, and it has not stopped yet. That's the good news, so to speak. Okay, and then on that question 2C at position Y. So we still want to talk about Y. And it's especially about the charge. So we have to say one, what is the charge and why do we use that?
The charge is positive because alpha particles are positive and they're deflected, meaning
Okay, yep.
they're the same charge.
Genau, exactly. Huh? Plus and like or boson. Great. 2D. So we just jot it down. I is 3.5 picoampere. Would you know what how much picoampere is if you go into powers of 10?
Negative 12.
Okay, yep. Okay, so that's one thing. Then we want to know the number of alpha particles per second. So it's a flow passing at point in the beam. So how do we get that?
Maybe 3.5 times 10 to the power negative 12 equals the number times 2 times 1.6 times 10 to the power negative 19.
Okay, all right, yep, okay, yep. I just same thing. I just write it first as a ratio, right? So same, no difference to what you said. 10 to the power minus 12, and we have time, which is 1.6 times 10 to the power minus. That okay with you?
Yeah.
All right, okay. And then I just jump ahead. That gives us 1.1, 1.1 times 10 to the power of 6. So, yeah, we expect a big number. No, it's not such a big number ultimately. Just a million, basically. Okay, good. Very good. Question 3A. So it's a very typical one. Kind of, because we have a plutonium 239 absorbs a neutron, and then the following reaction may take place, because we know there it goes into statistics, into the now we want to know the values of A, B, X, and Y. In other words, just rewrite the equation. What element is forming, Chris? What elements are forming? Oh, sorry, I was jumping ahead.
The xenon, and I don't know what that is. The ZR.
Zirconium, yeah. Sounds like from a science fiction movie. Okay. So, yep. And we have 3. And so, and we need to know this and this. This, we need to know that. Okay.
A is 1 and B is 0.
Okay. A is 1. Oh, should take green. And how come?
Because neutrons have a relative mass of 1 and no charge.
Okay, all right. And hence how we can, okay, I can just add it of course here as well. And what about the elements?
So y should equal to 94 minus 54.
Yep, okay, yep.
So 40.
40, okay, yep, good. And then xenon? Oh.
So 139 plus 1 equals to I'll just say x
239, sorry.
Oh, it's okay.
39 plus 1, yep.
Equals to x plus 103 plus 3.
Yep. Okay, 3 times 1, yeah, exactly. All right, okay. Enters x. Very good.
240 minus 106.
Yep. Six and
134.
134, huh? Yep. All right. I mean, this is kind of more algebra in that regards than physics, but not as a question, of course. Right? You have to put together the right pieces. So the interesting thing is that you can say, okay, I have plutonium. I mean, on the other, that means I shoot a neutron at the plutonium. What I get is it basically disintegrates, forms two new elements, and emits three neutrons, right? So when you think of it from a practical physical point, you need to have, of course, all the detectors in place so that you can measure what we are just talking about, right? So that you can see that or feel that or measure it, especially the neutrons then, of course, right? The elements, okay. Sometimes the trouble is that these elements have a very short half-life time eventually, not these two, of course, others. And so they're very invasive, and you need to really have the apparatus in place. Plus, you have to make sure that whatever you measure is not wrong, it's obvious, but in the sense of not influenced by something else, cosmic rays, surrounding atmosphere, whatever. There's a lot of potential damage which can happen, and of course that's why it's always so important that all these results are reviewed by peers, that they can redo the experiment based upon the description of the other scientists gave. They come then basically to the same result. Huh? So just that as a insight. Okay, so B. What is when you talk about fission? So first of all, just quick question: what is fission, Chris?
The splitting of the nucleus.
Okay, yep. And what would be the opposite?
The fusion.
Yep. Which would be then, in simple word,
Combining.
combining, merging, yeah. And interestingly, when you look at all the stars, they do fusion, they are not doing fission, actually. So any star does fusion, and they burn off what we call sometimes the burn off, right? And at some point we say the fuel has exhausted, so that means the star is collapsing ultimately for various reasons, which we look into in the solar report. And the reason, let's put it like that, why we have different elements is because they are formed in the heat of a star. And it's a bit too simplistic, but that's basically the core, because we know we have a hydrogen, the next level is helium, and so on. Typically, when a star reaches the stadium of carbon, then in tendency it starts to burn out. There's not enough hydrogen at the end of the day. It's like a decay because it's fusion. You lose the burning because it generates new atoms, new elements, and that's how, in the end, the star will die out. It all starts with the hydrogen and goes into the helium. When the helium content is already comparatively high, then we know, or actually the scientists could estimate already quite well, what is the probable remaining lifespan of a star by knowing already that ratio. So that all goes back to what we have just discussed. Okay, I would say we do this one and then we move on. A plutonium again, a 239, has a mean density of 1.3 times 10 to the power of 17. So we know that is a nuclear extremely dense and high energy content. And now we have to prove, typical question, show data. That always means we have to recreate the calculation and come up with the same result. So how do we do the calculation, Chris?
Have to find the volume first.
Yeah, I mean, there's various ways. It's fine. Yep. Okay, switch to blue. Okay, volume, yeah. There's more than one way to look at volume. So which formula would you now list, Chris?
Oh, wait.
I mean, you need volume, that's for sure. It's just that you need a bit more. Volume is a good start. Because you want to know about the radius, right? So clearly you need the radius, or the other way around. You need volume. Probably have to tend to use that further. So yeah, just what is volume? I mean, in terms of a formula, not the values.
Wait, I think we can use the method of finding the mass of one nucleus and then dividing the density, divided by the density.
Okay. Yep, can do. Okay. Well, and then, okay, yeah, let's go from there. So what is volume?
Volume is density divided by mass.
Is that correct here what I wrote, or is it not yet correct?
No, wait, no, because it's mass divided by density.
Exactly, okay, yep. So in other words, depends on mass divided by density is volume. I mean, when you talk to somebody and say, if I divide mass by density, I get volume, what would maybe be a better way to phrase it? I mean, of course it's correct, but what would be maybe a better way to phrase it? Of course it's the same. I mean, please don't get me wrong, but in terms of just to tell somebody and say, hey, we are talking about this and that, it's equal to that. What would you say is a one good way to say it? Or
when we have a mass, we divide it by the density, which is the amount of mass that occupies a unit volume. So
Okay.
if we divide it by that value, we get the number of unit volumes we can have for that
Okay, I
mass.
see how you go. Yeah, okay, all right. I mean, but I would have said, if I have to explain to somebody, say, okay, they know mass, right? Usually they say weight, but whatever, you're wrong. It has to be mass because that's kilogram without the gravity. Okay, all right, I get that. So we take mass, huh? They say mass. Okay, that's basically what many people refer to usually as weight. And if I want to say the density, what is density? Just in units.
Huh?
If I have to say the density, what is that?
The amount of mass per unit
Okay.
occupying each unit volume.
Yeah, exactly right. So exactly as I say, hey, if I have same density, right? That's something I can consider, for example, right? If I have kilogram per cubic meter, I can compare apple to apple because if something has a huge volume, okay, or it has a tiny volume, difficult to say. I just weigh it. That's the old story about feather and plate. So, so that means I basically just do. That is an easy way to explain exactly. So now, in order, we want to know the radius. So how can we link up all that now?
With the volume, we can find the radius.
Okay, yeah. And what is the definition of the volume, or how do I calculate the volume?
Mass divided by the density.
No, I mean, but I mean, when I say, okay, volume, how do you calculate volume on its
Oh,
own without,
the
you know,
4 over
on a
3
geometrical?
pi r cubed.
Exactly. Yeah? Because there comes the R into play, right? The rest are just constants, but of course they're needed, otherwise you have wrong volume and values. That's where we link it with the R. Huh? Okay. So we have a density. So let me just underline that. We have a density. And now, how do we proceed from here? What about mass? Do I know the mass?
Yeah.
How do I know the mass?
239 times
Okay, yeah.
wait
239. Sorry, not point. Two, 200. Okay, yeah. We know it has a relative atomic mass of 239. But
divided
that's the
by
relative. With
is
what do I
this
multiply it? What is the number 239 representing?
grams per mole?
Yeah, you're right. In this context, it won't help you. It's just straightforward. When you look at your periodic table, what does plutonium 239 mean anyway? By the way,
Uh, the relative atomic mass.
okay, and what does it mean in parallel?
Huh?
Because 239, yes, it's a relative atomic mass, and how is that mass formed? What contributes to the mass? What makes up the mass?
The nucleus.
Yep, and what does the nucleus consist of?
The protons and neutrons.
Exactly. Huh? And do the protons and the neutrons have the same mass?
Yeah.
That makes our life easier, right? Otherwise, we would need a second equation. So, therefore, with what can I multiply my 239?
Uh, the mass of a nucleon.
Yeah, exactly. And what is that mass? Or you can may say a proton or a neutron. It doesn't matter, right? Because they are the same mass.
I forgot. So I was
It's fine,
thinking.
no problem. You don't. That's fine, Chris. You don't need to know that by heart.
Because I
So
was
that's
originally thinking that we can divide the 239 by uh, the Avogadro's constant.
yeah. The 239. Okay, I see. Yeah, because you come from the mall, right? Okay, I
Yeah,
understand. Um, because you want to know the mass, um, you just make a detour and come back to the same, right?
yeah.
Because the 239, yes, it consists of 6.02 times to the power of 23, but then you have to come back still to the okay, yeah, should be the same. Let's do that. Um, so you say 239 divided by 602, huh? So 2 plus 607.
It's 0.239 because it's kg.
Okay, yep. So you get how much? What is the mass you get, Chris?
Uh, I get 3.97 times 10 to the power negative 25.
Okay, all right, okay. Yep. So two ways. Not always, but sometimes. We keep the same part. Okay. Six, 4 times 10 to the power by 30 kilogram. Okay. So that was one way, and we have the other. Very good. Okay. So now we have the mass. So mass has become green. Mass is green. So answer, and you know the density. The density is green as well. So how do we get the radius now?
Uh, Find the volume.
No, you may. Yeah, I mean, you need to know. We want to know R, huh? So that's why sometimes the color helps. Huh? I know the density. I mean, I have a value for it. I have the mass.
So it's the
And
mass over density equals the 4 over 3 pi r cubed.
okay. So what does that mean for me?
It's the volume times 3 over 4 divided by the pi and then square. I mean cube
Yep.
rooted.
Yep. Exactly. Yeah? So let's make that into one. So we have consequence 3/4 pi. Get mass. Okay. And we get for the radius, just to quickly say, so basically around 9 times 10 to the power of minus 50. So that's the radius of the plutonium. Okay. So what you can see here, I mean, it's obvious. This the the physics behind is more standard actually. What we quite some of that we know anyway from the basics, right? For example, this one, or you know what that all means. That is a bit new, the emission or the forming of new elements, but goes back to what we already have to know as well of how they are built up. So it has a lot to do with math in the end. in order to rearrange the respective formula. Okay, I leave those questions aside. Anyway, there's only just three. Maybe we have not dealt with that. We have discussed it last time explicitly. We have not done really any exercise with that, so today we do. This is but we have not looked at such a diagram. Have you seen such a diagram before, Chris? The N and Z.
Yeah, from a question.
Okay, all right. So, I mean, that's a very typical way, right? You can see, I mean, they can become more complex then, especially when you look into decay over various stages of what happens that we get to see that involvement. Of course, we have C and D. So here we have typical, we have N. Let's forget about which type of decay we are talking about right now. What does N stand for?
Nucleon number.
Okay, which means?
Number of protons and neutrons.
Okay, all right. And Z Hensworth, yep.
Then
what?
Number of the protons.
Yeah, exactly. Yeah. So that is obviously very important in regards to when we talk about this decay or looking around. Could be the fission, fusion, either way, depends on what we're talking about. Now here we talk about decay, we talk about beta minus. Okay. So we have a two-level decay. That's very typical. Huh? So first we do one, then we do the second. So in order to do this question, what is a beta decay? And we have the alpha. So what is the beta decay? What happens when a beta decay happens, Chris?
Increases in the proton number.
Okay. And with the alpha decay?
Decrease in 2 proton number and 4 nucleon number.
Say again, sorry?
2 proton number and 4 nucleon number.
Okay, so basically, in other words, goes up by a helium. Huh? Oh, yep. Okay, so when we now start with the first step, we clearly have two steps, right? I mean, step one, step two. Which of the ABCDs does represent the first beta decay?
I think it's C.
C. And what happens?
Because at first it's a beta decay, so it increases in one the proton number.
Yeah,
and
exactly.
then the alpha decay.
Yeah, okay, that's right. So yes, exactly. Oh, cool. So what we can say, in other words, it becomes another element. So, or, I mean, if you do that really step by step, then we say Z must go up. Huh? So that means anything where Z goes down is not applicable. So basically, we could say now blindly it must be C, but of course we cross-check that. Is it really C? And what does alpha tell us?
Huh? Yeah.
So the alpha decay?
Alpha decay removes 2 protons and 2 neutrons, so it's 4 nucleons.
Exactly. So it reconfirms our qualified suspicion or assumption or whatsoever. Exactly. Huh? So we go. See it is. Okay. Sorry, question 2. What happens in 2? I mean, they're not that difficult. You just have to follow the path, so to speak, and do it step by step. That helps enormously. You can't just answer them like that. 2 stages. It produces, okay, X goes to Y.
B.
Sorry. YB. Okay. Yeah. YB. Sorry. YB.
Because all of them will decrease in number of neutrons, but
Okay.
for A, C, and D, they lose more than 1 neutron, but B only loses 1.
So the N minus exactly. The N loss. Okay. Good. Number 3. After that, we reached it as the last question. Then we go to, like promised, test paper. Yeah? And we, of course, that will cover totally different questions. So we just spend a little bit of time on atoms. So what is the key difference? Or so it says there's an isotope Rn and an isotope Pb. So what are we talking about in terms of elements, Chris? Is Rn? I mean, you could check it in the table. You don't have to know it by heart, of course. Of course, over time you will know what stands for, like Pb, or what is Pb.
Pb is lead.
Lead. Mm-hmm. Okay. Yep. And Rn.
Radon.
Radon. Exactly. And radon is actually not to be underestimated. What is radon? What is the typical form? When you look at the periodic table, which group is it?
Radon is a noble gas.
Exactly. Exactly. Now, contrary to many other of those, it has a decay, and or let's say radon. Do you know? Let's say actually any building in the world doesn't really matter. Hong Kong is a bit even worse. Is there radon in as a gas around in buildings in Hong Kong?
Huh?
Radon gas. Is it in Hong Kong or in any place of the world? Let's focus on in buildings. Is it in our apartments? You can't just answer from, of course, from out. I mean, like that. It's a bit a question of have you been aware of?
I think so.
Okay, yeah, all right. You know, the tricky thing is that whatever we build out of rocks. We grind them, we make them into bricks or whatever, or concrete, doesn't matter. That stuff always releases then radon gases because it's in the earth. And Hong Kong is a bit worse than other places because of the material we are using for buildings. So the radon release of radon gases is comparatively high. The only way to move it is to move the air out of the room. So you can do that in 2 ways, right? You can either do a filtration, a ducting system, like which is sucking it out, so to speak, or you open the window. And then you check at some point for indoor air quality as well from the government, for example, it says we should on a frequent base actually ventilate in order to release radon because it's radioactive. That's something which many people don't really know or not really aware of. It's not the same as plutonium or something else, but it is radioactive and it affects the health, huh? Just as a side remark. So it decays. That's of course that's why it's radioactive because it decays, and it's waves in that context. Now it goes from 86 to 82. What does that tell us? What must happen? Now, unrelated to the question, when we see an element, it reduces itself from 86 to 82. So what did it release guaranteed?
Alpha particle.
Okay, or when you say from 86, from 82, how many? Well, what did it really, when you look at 86 to 82? Or it must have been gone somewhere into the environment or what?
The mic is a bit unclear.
Okay. Can you hear me again?
Yeah.
Okay, sorry. Yeah. So when you look at the radon to the lead, what is the main difference so that you can say this is radon, this is lead?
The number of protons.
Okay, so what is the difference in protons?
4.
4, right? So it must have had emitted 4 protons. And when you look at the total mass, so what is the delta M, so to speak, or the relative atomic mass change?
It's 16.
16. Huh? So we have a change of a mass of 16. And we know, on the other hand, if we lose 4 protons, we probably lost how many neutrons?
4.
Protons, yes. Neutrons?
If we're looking at mass, then there should be 8.
Why 8?
Because half of it is neutrons.
I see where you're going. When you look at the number, so we know, so we don't know what we have, right? We have X and Y, so to speak, but we can say that the relative mass of the one is 222 and the other one is 206. So we lose 16 grams, or in that context as well, we can say 16 particles. On the other hand, we know that in specifics, we already know that we lost 4 protons. So what else must we have lost? And how many of those? Otherwise, we won't lose 16 in total.
The resultant loss of neutrons should be 12.
12, huh? Okay. If it's important or not, we'll see, right? So to speak. So guaranteed 16 is an important number. 4 will be an important number. So what do we know about an alpha particle? You mentioned it before. What is an alpha particle, Chris? Or
Two protons and 2 neutrons.
Okay, huh? All right. 4, 2, huh? Okay, so that's why I said we may or may not need the neutrons. So if we look at the protons 2 lost, so how many? So we have 2 neutrons, protons, huh? So that means we lost how many particles? I put that one. When we move with an alpha decay, by alpha particles, so we lost how many particles? And how much mass did we lose?
4 alpha particles.
4, huh? 4. And how many did we lose in total? Or the total mass lost? So yeah, okay, you said it already. Yeah, okay. So there's various ways. So okay, yeah. So we lost 4 alpha particles. Huh? 4 out of 16. Because whenever we have an alpha decay, we lose 4. We lose 16. So okay. And Ainsworth, we know, and the question is the number. We want to know the number of stages, huh? So, how many? The difference in atomic number is how much? You said that already. 4.
Huh?
So we have therefore 8 protons released, huh? From the first stage, right?
So
Would have I have to be very precise. Would have emitted 8 protons, but how do we know?
the positron release.
Okay. All right. Okay.
Wait, no. Because, wait, 8 is lost, then we have 78 protons, then we have to lose the normal beta particle.
Okay.
Lose 4 of it, so we turn 4 neutrons into protons, and then we have 82 again.
Okay, cool. Yep. So, in consequence?
8.
8. Great, very good. That's a pretty challenging question, to my opinion. So basically, based upon such information, you have to conclude, deduce, that you have in the end 8 stages. Exactly what you said in the last 2 sentences. Okay, good. All right, so as we said, we leave that aside. No questions. And so on. So I'm just going forward. So there's limited fundamental particles, and now here we go into a process. And of course, there's, as we know, we have various papers. So we start because it's. Do you remember or do you recall, Chris? What is paper 1 about in terms of level, content?
I'm not sure.
Okay, so it's AS. Huh? So it's basically you will have another paper later on, which is then covering the higher level, or let's say the standard A level. But you make the first paper as well. And so the first one may be, because it's for AS, so you really have to cover the fundamentals, which most likely you have covered well. But let's go to the paper. So in case you wonder, okay, isn't that depends a bit how you feel about it in the end. Paper 1 is for A students. Of course, it's a base. You go further than the next. Nevertheless, you must do it. So let's go and do it. And we see which questions they eventually apply. Let's start with 1. So which one here is now a physical quantity?
A.
A physical quantity.
Physical.
It's not so actually. Some of that is kind of easy, but not easy in the end.
Spring constant.
Yeah, spring constant, exactly. You really have to think about it, right? What do they really mean by that question? It's not a matrix, it's not a dimension. That, of course, will lead, but you really have to look at the question very carefully. Okay, so which two units are identical when we have to express them in the SI base unit? That's, again, always, the multiple choice questions are sometimes quite time consuming because you have to walk or work through the various potential answers. And not all of that can be easily dismissed.
So joules is kg meter squared per second squared.
Okay. Yeah.
No, I don't think it's correct because.
And then, no. And then, because you have joule seconds now, not just joule. In B, for example.
But C can turn into A and S, then that would make S to the power of -3, but here only 2.
Yeah. What about, go back to B. I think you choose a very good one. But you just think that you will have to, right, when you look at it, you multiply it with times second, times, not per.
kg meter squared seconds to power -2, and then times S is
exactly
seconds power -1.
Yo. So they are not so straightforward in that regard. So it's not like, Newton meter, okay, that's quite straightforward. But it's not the right answer in that context, of course. Joules per coulomb, okay, yeah, all right, we can see that. Joule second, yes and no, right? You would rather think of joules per second, something like that. But joules multiplied with second, a bit less. So that's why. But you come from the right angle, absolutely. Say what is what, then link it. Then, of course, it has a bit of a trick in that context, times s. Okay. So we give a value for the acceleration of free fall on Earth. I will say 10 meters per second square. And of course, it plays now with what we know from. We really need to know the definitions. Basically, plays around with accurate and precise. In other words, what does accurate mean?
Accurate means it's close to the real value.
Yeah, it's kind of correct, within limits, so to speak, but close, like you say, close. So we obviously we need to choose a statement which says it's accurate. So yeah,
accurate but not precise.
Yeah, exactly right. Because we know it's not precise. Of course, it plays with the know-how we have. That's why. First of all, we have to know 10 is a good value because we quite often simplify it. We say, okay, value of 10 is good enough. Obviously, it must be accurate, but clearly it's not precise. So this one is not so difficult, but it gives a good idea of how the wordplay goes sometimes. And then it's a question of what do I choose first? Accurate or precise? It depends a bit on what you have here, right? So here it's easy, kind of, because free fall on Earth, you really know it's 9.81, 10, whatever. So this is a value we can refer to. So then we can say, okay, let's take that as the starting point. But another question about accurate and precise maybe we have to deal with quite differently. Okay, now here comes something with calculations, of course. You see that as well, Chris, just to briefly go back. You have 75 minutes and you have 28 questions. So you have not 3 minutes, less than 3 minutes per question. Clearly, some of them you will need less than that amount. but it will be needed eventually for something else. Huh? So it gives you a good idea to keep that in mind. Not to panic, of course, but still to say, okay, there's a certain time limit I spend on it. Okay, so question 4. If I would have to draw something here first, what would I have to draw, Chris? What are we looking for?
The vertical and horizontal for each force.
For each force, or can you just look at the question again?
I'm saying that for each force, and then we add them.
Oh, no, okay. Yes, okay, you already got that one. Okay, fine. So what we look at this one, right? Okay, that was of course highly imprecise. Okay, so right, we're looking at the result. So it helps to draw it. That's what I want to say. Even if it's not explicitly being asked, good to draw it because then everybody knows this is the result, and so the student clearly understood what it's all about. And so we want to know now the horizontal and the vertical one, right? So in other words, I mean, of course, we go a good way. So when I look at my horizontal one, that would be my horizontal one. That would be my vertical one. From the result. Horizontal result. Okay, so how do you go ahead now, yeah?
I find the vertical first. So for the 15 one, I find 15 times sine 20.
Okay.
5 point.
Oh, sorry, my bad. Oops, sorry. Like that, okay, yep.
5.13.
And 1, 3, okay. So I give that. And what is your plus and minus direction? Because that's makes a big impact.
Plus.
Plus, okay. So we say plus plus like that, huh? Of course, you could do it the other way around. Doesn't matter, because they are all relatively at the end of the day. Huh? Okay. So we talk about the plus force here. Okay. What about your second one?
I think it's easier to directly do the horizontal for 15. So
Okay.
just 15 times cosine 20.
Go. Okay.
And then 14.1.
14.1. Okay. So here is 14.1 plus as well. Okay.
And then for vertical of 6 is 6 times cosine 40.
Yep.
And then 4.6.
4.6. Okay. So
It'll be
minus.
Yeah. And then horizontal is 6 times 6 times sine 40.
Okay. Yep.
3.86.
Okay. So now adding up horizontal and vertical. So, or which one? I mean, it doesn't matter which one first, right? But if you add one, I like what you did. Now, when you add them together, let's say the horizontal, for example, right? Because they're both plus, makes life a bit easier. Just add them up, so you get something close to what value?
When I add the vertical, I think it's because of the significant figures.
Yup.
We only get 9.5.
Yup. Okay, well, let me just write that down. Sorry. So we say R horizontal. So if I talk about R horizontal, right? So what is the value roughly? Say it again, please.
Wait, no, no,
R
no,
H.
no, no, no. Oh wait, no, 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 I mixed it up.
Yep.
Horizontal is 14.1 plus 3.86.
Yep.
So 17.96.
17.96. Yeah, okay, exactly. And what do we have as choices?
C and D.
C and T. Okay. Yep. So we say C and T. Now if we do the well, that was a very good
0.
encoder choice, but okay. So our, our vertical is how much?
0.53.
0.53. So, or in other words, it's plus 5.13. Yeah, you're roughly right. Minus 4.6. So we talk about, say the value again? 0.53. Huh?
Yeah.
So, okay, so clearly we have this one, and on the other hand, we have the blue one. Huh? Okay, so we talk about 4C. Yeah, very good. So, I mean, this one, you see at some point you can basically jump ahead and say, wait a minute. If I have 18, right, as what I calculated, must be about 18 for the horizontal, then no way it can be 10 from what I already or what we already calculated, right? Because one is 5, the other one is minus, so they are very close, but in opposite directions. So there must be a very small difference as a result. No way it can be 10. So there you can already jump ahead. It's not a good idea, so to speak. But if you would be in a speed contest, then it would be worth to jump ahead and say 0.5 because no, they are nearly annihilating each other. Nearly. There's only a tiny little force still going in that direction. Okay. Now number 5, the velocity time graph for a car starting from rest. Now we want to know the average acceleration. Or in other words, what do you see in the chart? Actually, what is the curve representing? If you look at that curve first.
An increasing acceleration.
Okay. So, okay, in 2 steps. What is it? Yeah? You're correct. What is it first?
It's a curved velocity.
Yes, exactly. Yeah, that's good. So it's an increase in velocity, but it's non-linear, right? So hence it's an acceleration. Yes. Huh? So that's otherwise, if I would have a line like that, what would it be? Would there be any acceleration?
It's constant acceleration.
Oh, sorry. Yes. Is there an accelerated acceleration? Exactly. Huh? No. You're fully right. Exactly. Huh? And this one indicates an accelerated acceleration. Huh? So, in other terms, when you go into math, it's then just the derivative of the acceleration, even actually, not just the derivative of the velocity. Okay, now we want to know the average acceleration of the first 5 seconds below the curve PQ. So we're talking about this one. Sorry, I just said A. Sorry, my bad. What is it? Which one is it now? The area or the gradient? I would. No, I better let you answer the question. Sorry.
It should be the area below the triangle. US.
The average acceleration.
Yeah.
When you get what is the air? Is it the area underneath? Is that
Oh
the
wait,
average
wait.
acceleration?
It's no, because it's
Mm-hmm.
q minus p divided by 5.
Okay, yep.
So then it should be the gradient of
Yes.
PQ.
Yeah, very good. Exactly, huh? Very good, very good. So, because, I mean, regardless, if, and that's why I was saying that at the beginning, I mean, regardless if it's like that or if it's curved, I mean, in a simple situation, if that's the velocity, this is and we say after 5 seconds, what is then that area representing, Chris? Assuming it's not, it doesn't matter if it's a curve or a line, but for simplicity, let's say it's a line.
The distance
The
traveled.
distance, exactly. Yeah? And that won't change, right? Even if it's a curve, it's still the distance, but we can only make an approximation that we say, okay, you know what, a line is only a slightly bent here, it's a bit worse. So it's okay, I take that line. Or if I want to be accurate, I maybe split it and say first this line, then this line. Huh? So I split it into two areas. The distance, mathematically speaking, so to speak. As if I have a non-linear velocity or an accelerated acceleration. Underneath, it won't change. You still have the distance because we're talking about velocity. That may be sometimes a bit tricky, but I think of, I have an accelerated velocity, a velocity which is increasing, but in parallel it's non-linear, so I have an accelerated acceleration. And suddenly I may become a bit fuddled and start to think about acceleration. Then if I would replace that with acceleration, integrated over time, just as a question, what would I get, Chris, if I say this is not math, sorry. So if you don't feel comfortable, just tell me. If I would say this is now acceleration, assuming you have this one, it's about linear and non-linear. So acceleration is steady. What is underneath what is the area when I replace velocity with area and sum it up over time? What is that one representing? This one is acceleration.
Increase in velocity.
Exactly. No? So it's always the same principle. So it's very, very important that we look at and say, what are we talking about in the chart? It won't change. It's still velocity. Doesn't matter if it's linear or non-linear. So underneath the curve must always be time at distance. Excuse me. Okay. And now you realize that, and therefore the gradient of the straight line. Because we talk about average. Sorry, that shouldn't have been crossed out. Average. Huh? If it would not be average, so that's why these multiple choice questions have a lot to do with workflow. And did you have differentiation already, also calculus?
Huh? Yeah, in math I did.
Yes, so that's why, of course, therefore, of course, the wordplay is justified. That we say average, then of course, then we approximate it with a linear, so with a line, instead of this one. Otherwise, you would have to make the integral of the difference of the differential. Huh? Okay. Let's see. But of course, we can in the end deal with any question. But I would say, let's see. Okay, there's a lot of velocity, density, pressure. Okay, of course, because it's AS. Maybe let's go to question number 9. Every question we can do, of course, in the end, but let's do this one, number 9. So a projectile is launched at an angle and travels through the air, and we see the typical path. The question here is interesting because it says, which diagram shows the direction of the force or forces at position X? It's an interesting question.
B.
Or B, okay, yeah, all right. And why?
At that instant, it's moving horizontally, and there's air resistance towards its left, and then there's also gravity.
Okay, huh? Good. So, what did the typical question when you have to calculate something quite often then says dismiss air resistance, right? Because otherwise we can calculate the reaction, but that's not the question. So that's why here we have to be careful that we realize, oh, they did not say dismiss anything. And if you would have to dismiss anything, like say in order to calculate it, which one, I mean, I more or less answered it, but what would we then dismiss? Which one of the forces would we dismiss?
Upthrust.
Mm. At X.
Huh?
At X. You still have an upthrust at X?
Yeah.
Why does it then not climb higher?
Because the magnitude of gravity is larger.
At X? What? I mean, you're close. But what is in equilibrium at X? I mean, why does in other words, why is it not still going higher? Why is it starting to go down here?
Because the force of gravity overcame all the momentum, upwards momentum.
Okay, yeah. And what do you mean that when you say overcome in other terms? What are these two forces? What is happening to the sum of the two forces at X?
They cancel
Y
out.
direction. Exactly. Huh? That's very important. So whenever we talk about, we always put it into X and Y. And clearly it doesn't go higher, so it must be in balance. Otherwise, no way it would not continue higher, or it would already descend earlier. Either way, right? So that's why point X is exactly the one where the two forces are in equilibrium. However, so that's why when we sometimes see it, say, okay, the upthrust is there, but because it's over time ultimately, yes, it's over distance, but that is over time as well. So the gravitational force starts to increase, right? Because we know it goes over the square. So obviously it will grow from zero over time, become bigger, sorry, the other way around, bigger and bigger and bigger and bigger, until the one which threw at the beginning, this one upwards, is annihilated. So they must be in equilibrium. Huh? So the question here is a bit a different one. That's why it's important to remember. So if you would be in space, far away from any massive body whatsoever, and well, okay, there's action, reaction, and so on. But if you would now throw up something into space, forget about your point of start, and you throw it up in that direction, in which direction would it go on without any gravity?
Huh?
So you launch it like that. I mean, in space somewhere, far away from another gravitational body. So in which direction would therefore the projectile go?
Towards the body.
Okay, yeah. I mean, there's the action reaction issue. So assume now, for whatever reason, you have a solid situation here, and then it goes out like that. Would it continue like this forever, or would it start to bend at some point?
If it's upwards momentum can overcome gravity until it escapes the
Yeah, okay.
gravity.
And if there's no gravity?
Oh, then it will continue.
Yeah, exactly. And yeah, I mean, completely, you have it, exactly. That is something we have to keep in mind. I say, okay, always Newton under the influence of an external force, or it's in equilibrium. Either way, it will continue, but then it accelerates. You can pass them faster, or it's in equilibrium, but there's no other way, so it will always continue like that. Once started, it will go on like that. So the only reason it goes here, it must be overcome before it hits the ground. So that's why one of those it cannot be the case at all. Okay, let's see number 30. What does it play with here? What is the core of the question?
Moments and
Yo.
resulting force.
Yes, exactly. Okay, good one, right? So realizing that helps a great deal, of course, to answer it. So Ainsworth force at P, what will happen as the person moves from Q to R? So obviously goes out here.
I think it's easier to focus on P first.
Yeah, okay, yeah, please.
As the person moves towards Q, then his moment decreases, so the resistance that P has to the rod on P has to provide is less.
Okay.
So force at P decreases.
Okay, yep. And Ainsworth.
So at Q, the resultant force is the magnitude on P and the magnitude of the person.
Okay, so does it decrease or increase?
Decrease.
Decrease, right? I mean, when you think of the pivot point, right? I mean, of course, it's a bit split, but in tendencies, it just means as the person moves, then of course, that's why I started like that. But of course, you do it like you do, that's fine. It decreases that one, and as it decreases this one, it must decrease that one. But you can go from two angles. That's good. Okay, let me go back quickly. Maybe, well, maybe let's do number 8. Number 8. It comes out from a pipe at velocity v, hits a wall, has a cross section A. What is the force of the water on the wall? With the known parameters. That's the key, of course. Or how do, in other words, Chris, how do you get a force on the cross section in general?
Mass times the acceleration.
Acceleration, okay, that's one way. What else? How else could you define a force?
Change in momentum over time.
Okay, yup, do that one. Delta is always a bit initially delta t. What else when you look at here with the area? Somehow we have to bring in that cross section. So what is the force as well? When you think back.
Pressure times area.
Pressure times area. Okay, so that's why, right? In this context, we somehow have to bring in what is given. Um, so obviously, when we look at the result, area is a factor in all cases. Can we exclude already one of the ABCDs from that relationship, most likelihood? When you look at
A
what
and
he
B.
just said, yeah, because it must be multiplied by the area, right? I mean, from what we see here, because they all deal with density and velocity. So the question is now, obviously, how can I identify something for pressure, right? And now comes the density into play and velocity. How do I get pressure?
Density times velocity will give momentum over area.
Okay.
Or no. Momentum
No.
over volume.
Volume. Yeah. Mhm. That's one thing. Is that now when you look at the result, how, because in such case it's always helpful to look at the one of the given answers, right? So in other words, the question is it density times velocity or density times velocity? Or in other words, what gives you density times velocity in
Density times.
practical terms? Say again, sorry?
If we times another velocity, then it will become force over area.
Force over area, huh? So um, when you have, so density is mass over volume, right?
So then times velocity is momentum over volume. Times another velocity is cancel out the one dimension of the volume,
Okay,
and
yep.
then you have per second, so it's momentum per second per area and force per
Okay.
area.
Okay. So in consequence, what is the answer?
D.
Yeah, yeah. Yeah. So yeah, exactly. So this is, I mean, it's already quite something, right? It's a matter of which angle you choose for the answer. I mean, you can come from various angles, try to visualize it to some degree as well, which may become a bit difficult. Or you say, well, velocity leads to volume, right? Because it increases. So typically, when you have a pipe like that, and it moves forward, so it starts to form a volume, right? So with the area. So that's why the classical area times volume always leads to volume. Right? Something interesting that good to keep in mind. So the higher the volume, of course, the more you have. Sorry, the higher the velocity, the more volume I create. Or of course, I increase the area, then of course I need less velocity. And from a practical point, please, maybe if you look at that, we have that as well, but we can just cover it as well. Say, I have here this one, other way around, sorry, something like that. And I have V, or I do this, and I say I create the same volume. So which one has the higher velocity? If you compare those two pipes diameters, so which one must have the higher? And I say both transport the same volume.
Then the smaller one, the narrower one would have higher speed.
Yeah, exactly right. Exactly. I mean, it's quite obvious, but that's interesting to realize because if you have, say, a current and you go from a wider diameter to a lower one, for the smaller one, it starts to accelerate. It's kind of obvious, but not so obvious. That's why you may have erosion, for example, in a river. Then you start to have the river grows like that, and then you start to narrow it down. But of course, the velocity increases. That means that here you may have some, let's say, in these areas, some erosion because of that result. It flows faster. But on the other hand, it's a way for you to achieve a certain effect if you want that, because it's an acceleration. And for acceleration means force, and hence you may have some problems here. When you look, however, and that's always a good one to say, of course, it must be like that because you have the same mass, right? The mass which is going through here is the same mass as going through here. That's another way to look at it. That is my mass, the mass per time must be the same. Hence, the only way to get that is to accelerate. When you look at people behavior, would you say that is true for people usually as well?
Like a crowd?
When you have a lot of people, say, in the MTR, and then you go towards, let's say, the exit, and the exit is narrower than where they come from, do they rather accelerate or slow down?
At the exit, there would be faster flow.
Pay attention next time, Chris. Usually they slow down.
Huh?
Funny enough, right? When people come towards the exit, and all the people start to come together, they usually start to slow down. So if you have, for example, an escalator, that's maybe the best example. There's many people here, and only so many can go here. They start to slow down. They are not starting to run onto the onto the escalator. But if it would be liquid, it would accelerate. Of course, the reason people do that, they have a conscious decision. They decide not to walk faster.
Yeah.
Of course. It's a bit a different situation, but I think it's good enough to keep in mind. Huh? Okay, so for next time, Chris, should we just continue with such questions from the test? Yeah. And should we leave the past chapter 11 aside? No more questions for that one?
Yeah, we just focus on the past paper.
Past papers, okay. So yes, we can do more. Then we will do as well, of course, unstructured ones. And we do A-level as a paper 3 questions then as well. Huh? Oh, okay. Next Friday is actually Good Friday, so I guess you probably will have Easter holidays. Oh. But we still have it on schedule, huh? So, all right. See you in a week. Huh? Have a good week.
Okay. See you.
Thank you. Bye.
If we do paper 3. I don't know. We just don't do. Play the Minecraft. You already playing or something?